Hello people, this video is in continuation to the previous video where we learned about JavaScript, performance, just-in-time compilers, and in today's video we will learn about assembly level language. Okay, so in the last video I explained how us in how people like us write code in high level language and that code gets translated into lower level language that machine can understand. Okay, but how the machine understand this code that's in binary? So to understand how machine brain works, we need to understand the architecture of the machine's brain or the computer architecture. Okay, in a computer there are operations that needs to be done, say adding two numbers, subtracting two numbers. Those are arithmetic operations. Logical operations like 3 greater than 2, those things are logical operations. So these operations are need to be done, and the unit that processes these operations is called ALU, arithmetic logical unit. It's denoted by something trapezium with a triangle in it, like this. Okay. Near the ALU, there is a unit of memory, a short-term memory, small in size but fast accessible, very fast to access for the ALU. These are called registers. These are the places in which values of the, say, adding two numbers 2 plus 3 will be stored. Okay. And a long-term memory called RAM exists to store longer instructions, longer sets of instruction. The programs itself exists in RAM. Okay, so that's the architecture of a computer, of the machine. Whatever the uh, translation like this is a translation is received by machine is perceived differently according to the architecture of the machine. Say x86 machine or ARM machine will understand the same piece of instruction differently. Okay, if I give this binary instruction to x86 and ARM, they will understand it differently. Okay, so here we have a problem then. What is the problem? Say I have a C language and I want to talk to machine. I need to be able to build a specific translation for x86 machine. The same is with C++, the same with Rust. And if I have a ARM machine now, then I have to build a specific translation for the ARM machines. So this process is, not efficient. What efficient could be is that we put an intermediate somewhat like this in between, where every code will compile to this intermediate language and will uh, will then be processed or converted according to the machine which on which it's going to run. Okay, so this part where the C language will be compiled to IR, the intermediate representation or called assembly language, is part of the code, is part of the process called front end. And when the IR, that is assembly language, will be processed to specific machine targets, x86 or ARM, that is the uh, part of the process called backend. Note that we used mnemonics here like add, R1, R2. My machine received this piece of instruction, and according to this specific machine, after the 3 bits, it takes 1, 2, 3, 4, 5, 6, 6 bits as an instruction that what it has to do. It has to add, or it has to subtract, or it has to compare. Whatever instruction it has to follow is written in here. Every instruction will have a unique set, a unique code, and the more sets of code the machine has, the more versatile is the machine. Essentially, you can may say i9 machine will have more instructions, more sets of instruction than a dual core or Pentium machine. Okay, so what this machine does when it reads this type of code is that add 001 is the address of the R1 register, 010 is the address of the R2 register, add R1 to R2. Okay, but this was specific to this machine. Another machine could have just read first 9 bits as the instruction, so this may be different for that machine. Okay, so we will translate the C code into a middle layer or the intermediate representation, which will be something like add R1 R2, and this is called assembly level language. Okay, so this is it for today, and we will see you in next lecture where we will discuss WebAssembly.